Welcome to the physics class for November the 17th. Before we talk about last night's homework, let's go over a couple important announcements. So first of all, quiz 6B is now unlocked and you can go back and retake it now as many times as you want until you get a perfect score. Now you won't be able to get a 10 on it anymore. If you want to get a 10, you got to get a perfect score before the deadline. But you can get a 9, and that's pretty good. And later today, I will unlock quiz 6C, the one that was just due a few minutes ago. But I need a few minutes to look at it just to give me that kind of feedback that I need to let me know if you guys are getting it or not. Also, don't forget that Engineering Day is this coming Saturday at the U, except it's going to be held online, but it's run by the U, and I will give extra credit for that, so don't forget about that. Also, tutoring. We've almost got things worked out. Mr. Wilson wants to do things a certain way, which is a little different from what I had previously set up. So the plan is, as of right now, is that we will be doing tutoring after school on Tuesdays and on Thursdays. And then on Fridays, during the middle part of the day, we'll be doing tutoring. And we'll have students who took physics last year or the year before, who are really good at physics, and they will be your tutors. So the first one is scheduled for today after school. I wanted to do it just in my Zoom room, but Mr. Wilson is saying that he prefers to do it differently. He wants to set up a separate Zoom room that everybody goes to for all tutoring on all subjects, be it biology or chemistry or English or what. So we're still working out those details. I will send you an email before the day is over telling you which Zoom room to go to, but there will for sure be tutoring today after school, starting about 3:45 and going till about 5 o'clock. And so look for an email telling you where the Zoom room is going to be that'll be done in. And then also Thursday after school, we're going to do another tutoring session. And then Friday from 11:30 until about 12:15 or so, there will be none. So we got 3 tutoring sessions per week set up. Please take advantage of these. If you don't take advantage of these, Principal Wilson is not going to keep on doing them. He's paying the students to do this. So you don't use it, you lose it. Okay, and then the last thing is that today we are going to do some more in chapter 7, but we are not going to finish chapter 7 today. So we'll wait and we'll finish it next time. And in theory, if we wanted to, we could take the test on chapter 6 and 7 next week, right before Thanksgiving. But I don't think that'd be a good idea. Based on what I'm seeing from your quiz scores and other feedback that I'm getting, I think that you guys would appreciate having a day of review before we do the test. So plan on the test being right after we get back from the Thanksgiving break. That's the plan for now. Okay, now before I start into the new stuff, or before I talk about last night's homework, are there any questions about anything that I just went over? Okay, not seeing any, not hearing any. All right, let's talk about last time's homework. So here are the problems that weren't in the back of the book, except for problem number 1. We need to talk a little bit about problem number 1. There has been some confusion because of an error in the book in problem number 1. When we first bought the books many, many years ago, there was an error. Yeah, okay, so I see people are voting already for the problem you want to see. Okay, good. But while I'm talking here, I want you guys to start voting. So let me know if you could only see one problem, which one would you want that to be? But while you're doing that, let me talk about problem number 1. Okay, so when we bought the books many, many years ago, there was an error in the book on problem number 1. It said that Ganymede's distance away from from the planet was 32 days, when in fact it's actually only 7.15 days. So that's what the book said. And then as people's books wore out, we bought some replacement books, which we thought were identical to the original books. But later on, we discovered that the author had realized the mistake that they made. And so they had changed the number in problem number 1 from Ganymede's period not being 32 days, but they've made it be 7.15 days, which, by the way, is the correct period for Ganymede. And so depending on which version of the book you have, you're going to get 2 different answers. So if you have the older version of the book that says Ganymede's period is 32 days, then using Kepler's third law, the number that you should have come up with would be 29 units for the distance. If, however, you have one of the newer books where they've got Ganymede's period as being 7.15 days, okay, so then in that case, the number you should have come up for the distance should have been 11 units. Okay, so don't worry if you got a different number than somebody else did. Now, this came up during the tutoring session. Things got confusing during the tutoring session because somebody had one book and somebody else had a different book, and so they're saying, hey, what's going on here? Why do we get different answers? Okay, so Austin is saying that in the back of the book, they said it was 4. Yeah, so it's just totally screwed up. So don't worry about what's in the back of the book there. These are the numbers that you see right here. Okay, and so now let's see, you guys have been voting, and it looks like problem number 4 is hands down the clear winner here. A couple other people wanted to see some. All right, so let's do problem number 4 then. Let me open up a whiteboard. And okay, so in problem number 4, they're telling you that the moon is a certain distance from the Earth and it has a certain period. And then they're telling you that there's a satellite that is a different distance from the Earth, and they want to know what is the period of that satellite. Okay, so they want you to solve this using Kepler's third law. Now, Kepler's third law says that as long as you have 2 objects that are both orbiting the same central thing, it doesn't matter if they're planets orbiting the sun, or if they're moons orbiting some planet, or if it's some man-made satellite orbiting some planet. As long as the 2 objects that you're going to use in Kepler's law are orbiting the same central object, then you can use Kepler's third law. So Kepler's third law says the period of one of the objects divided by the period of the other object squared equals the distance of the first object divided by the distance of the second object cubed. That may not look like a 3, but that's supposed to be a 3. Let me, make it look a little more like a 3. Okay, there we go. Okay, and it doesn't matter which object you call A and which one you call B, but it does matter whichever object you call A, you need to put it on top, both on the left side and on the right side too. Otherwise, you're going to get in trouble. Okay, so in problem number 4, they tell you that the period of the moon is 27 point something, 0.3, 27.3, and they use days. And now notice that days is not a standard physics unit. The standard physics unit for time is seconds. So you might think that that's going to cause a problem, but as long as you use the same units on top as you do on the bottom, the units are going to cancel out. So if you don't want to do seconds on top and seconds on bottom, that's okay. You can use days on top and days on bottom. You can use years on top and years on bottom. It's okay, as long as you use the same units on the top as you do on the bottom. Okay, so now they're going to say the average distance of the moon from the Earth. And by the way, this is from the center of the moon to the center of the Earth. Whenever we talk about these distances, it's always from the center to the center. Okay, so they're saying that the average distance of the moon is 3.90 times 10 to the 5th. And the units there are kilometers, which is not a standard physics unit. But as long as we use kilometers for the other object, then we'll be good. So for the other object, which is the satellite, they are in fact using kilometers. So we're okay. So 6.70 times 10 to the third kilometers. Okay, so always check. Make sure that the units here match the units there. If they don't, then you got to make them match before you can stick them in Kepler's third law. All righty. So what we do then is we want to solve for the period of the satellite. So what I'm going to do is I'm going to, instead of my A's and my B's here, I'm going to make them M's and S's. And so I'm interested in the satellite. So I'm going to put the satellite on top. You could put it on the bottom if you want, but okay. So I'm going to put satellite on top and moon on the bottom. That just because it makes the algebra a tiny bit easier if I do it that way. All right. So I'm trying to find out what is the period of this satellite. Well, okay, I need to do a little bit of algebra. And if you've learned nothing else this year, I hope that you've learned that it's easier to do algebra using letters than it is numbers. So let's not put in the numbers yet. Let's do the algebra using the letters and wait until we get the end and then put in the numbers. Did I say, I may have come out wrong. Let me try that again. We want to do the algebra using the letters and then at the very end, put in the numbers. Okay, so I want to solve for TS. And so I've got a square here. So let's get rid of that. So I'm going to take the square root of both sides. And so then I'm going to get TS over TM equals the square root of RS over RM cubed. And then next thing I'm going to do is I'm just going to multiply both sides by TM. That cancels that. So I get TS, which is the period of the satellite, is equal to the period of the moon times the square root of the average distance of the moon divided by the average distance of the satellite. Those are the kinds of mistakes that'll bite you. Average distance of the satellite divided by average distance of the moon cubed. Okay, so now all we have to do at this point is just plug and chug. So the distance of the satellite, well, it goes right there. Distance of the moon, that goes right there. And they are the same units, so we're going to be good. The period of the moon, that goes there. Notice the units. The units on that are days. Okay, so when we put this into our calculator and punch it out, we'll get some number, but the number is going to be in days. Now, if you left it as days, I would be okay with that. But for some reason, the authors who wrote the book here, when I looked in the back of my book, because I've got the teacher edition, it's got the answers back in there. So they put the answer in terms of minutes, which I really don't know why they did that, other than maybe just it's a number that you can relate to a little bit easier. So 88 minutes, that's about an hour and a half, which, by the way, is a realistic number. If you were to look at the International Space Station or other satellites that operate in what we call low Earth orbit, that is, in fact, the right number. It takes the space station about an hour and a half to go all the way around the Earth. Okay, so I'm guessing that's the reason why they did it. So what you need to do is you need to take the number that we got from the previous page, which uses days, and then you guys know how to convert, right? 1 day is 24 hours, and the 1 hour is 60 minutes. So yeah, you can convert. Okay. And then part B, it says, what is the period of a satellite that's in orbit around the Earth? So B is the exact same thing, except that, this time, no, I'm sorry. Part B is different. Part B is saying how far above the Earth's surface. Okay, so for part B, what we have to recognize is that if this is the Earth and this is the satellite. The number that they gave us here in this problem, this number, which was for the satellite, they said that it's 6.70 times 10 to the third. Okay, so they want to know what is the surface above the Earth's surface, not the distance from the center. So all we have to do is just find out what is the radius of the Earth. So if we just take this number and subtract whatever the radius of the Earth is, then that'll tell us this number here. So it works out to be 320. Okay, so then where could we get the radius of the Earth? Well, if you read the book, let me skip ahead here. There we go. If you look in the book on table 7-1, they tell you, they got all the different planets here, and they tell you what is the average radius of the planet. So you can get it from there. Okay, so this table you see in page 7-1 is a very useful table. I would definitely recommend you refer to that one frequently. And let's go back up here. Okay, and then you'll notice that I have just a little reminder to myself here to discuss problem number 5. And the only thing I want to talk about that is that problem number 5 talks about a satellite that has a period that is exactly 24 hours. Well, that turns out to be a really useful satellite. In fact, we have a special name for that. We call it a geosynchronous satellite. So if this is the Earth, and here's the North Pole, here's the equator, here's the South Pole. So the Earth is rotating here. Well, how much time does it take for the Earth to rotate once? Well, 1 day, 24 hours. So if we have a satellite out here that's going around the Earth, okay, and the period of this satellite is equal to 24 hours, then imagine what that's going to mean. So if you are at this spot on the Earth and the satellite is directly over your head, that satellite is always going to be directly over your head. It's going to appear to you as if the satellite is not moving. Now, the satellite is, of course, moving because you are moving, you are spinning. But the satellite is moving at exactly the magic speed so that it will automatically stay above your head at all times. Now, why is that useful? Well, I'm sure that some of you guys have satellite dishes at your home. Okay, have you ever wondered how that works? So there's a satellite out there, and that satellite is in what we call a geosynchronous orbit. So when the company Dish or whoever it is that you get your satellite service from, when they point that satellite dish at the satellite, they never have to move it again. And so then they can beam signals to your TV and life's good. But they could only do that if the satellite that they're pointing at is in geosynchronous orbit. Okay. So Austin is saying that I froze up for a while there. Austin, oh, no, the others are saying that I didn't freeze for them. So Austin, it must be your internet, not mine. Okay. So I would like to do some more problems in theory, but in reality, we've got a whole bunch of new material we need to cover. So let's just jump ahead and let's go into the new material. So if you have questions about last night's homework that we did not have time to talk about right now, remember, there will be a tutoring session today after school from 3:45 until 5 o'clock. There will be one on Thursday after school from 3:45 until 5 o'clock. And there will be one on Friday from 11:30 until about 12:15, until 12:45. Okay. I don't yet know whether those will be held in my Zoom room or whether they'll be in one that Mr. Wilson is setting up. But watch your emails, and before the day is over, I will send you an email telling you where those tutoring sessions will be. Okay, so today we're going to do some more out of chapter 7. And as I said a few minutes ago, we're not going to finish chapter 7, but we will do some important stuff. Now, before I jump into the new stuff, I want to do a real quick review of some old stuff because you need to be really good and solid on the old stuff in order to understand the new stuff. All right, so first off, I want to make sure everybody understands retrograde motion. That was the thing that killed the geocentric theory. You know, people thought for a long time that the Earth was the center of everything. And then they realized, well, wait a minute, the sun can't be on the same celestial sphere that the stars are on, because that way the constellations that we see in the wintertime would be the same as the constellations that are in summertime. So there must be two celestial spheres, one for the sun, one for the stars. And then they said, wait a minute, there must be three because the moon moves differently. And then they said, wait a minute, there must be more because each of the planets move differently. Okay. And then they said, wait a minute, there's this thing called retrograde motion. And then they really started pulling their hair out because they said, how in the world can we explain retrograde motion if the planets are all on a sphere that is orbiting the Earth? So along came a guy named Ptolemy. He was a flat earther back before the Flat Earth Society ever existed. He came up with a mathematical model that was a little bit convoluted, but it kind of sort of worked. It kind of sort of explained retrograde motion that allowed the geocentric theory to still be semi-plausible. So here is Ptolemy's model of the universe, which you guys need to understand. All right, so what we've got here is, okay, the stars are all on one celestial sphere and it's turning at a certain speed. The sun is on a different celestial sphere that is turning at a different speed. And that's the reason why we see different constellations in the springtime than we do in the fall time. Okay. The moon is on a different sphere. Each of the planets is on its own sphere. So we got an awful lot of celestial spheres here. And then in order to explain retrograde motion, what he said was that the planets are not actually on this sphere. They're on a smaller sphere, and that smaller sphere is connected to the sphere. So we've got these two things called epicycles and deferents. So the planet is actually moving in a circular path here while the sphere that it's on moves like that. And so you can see here that there will be times where the planet will move backwards. And so you can see that Ptolemy kind of sort of explained retrograde motion. And it allowed people to continue to believe that the Earth was in fact the center of the universe, even though retrograde motion occurred. Okay. Now, the thing is that nobody had really made super careful measurements about where the planets were. They just looked at Ptolemy's model and they said, well, okay, yeah, it kind of sort of explains it. We'll call it good. Okay, but then along came Tycho Brahe. And Tycho Brahe spent all of his adult life, or at least a very large part of his adult life, measuring the position of the stars. He had these really cool instruments made in the tubes there. And so what he did was he measured the position of the stars for many, many, many years, and the position of the planets, especially position of the planets for many, many years. And his assistant, Johannes Kepler, took that data and then he compared it with Ptolemy's mathematical model. Now, I keep emphasizing this because this is so important. This is how physics is done. Is what we do is we come up with a mathematical, well, first off, we come up with a hypothesis. So the hypothesis is Ptolemy's model of the universe. And then we come up with a mathematical model. So we say, if Ptolemy's model of the universe is correct, then it is theoretically possible that we could calculate how fast each one of these spheres would have to be moving. And also the epicycle spheres, how fast the epicycle spheres would have to be turning. So we can actually come up with numbers for how fast everything would be doing. So we can come up with a numerical model. Numerical models are super important. So once we have a numerical model, then we can collect all of the data and see, does the data match the model? All right, so up until Tycho Brahe, nobody had good data. But when Tycho Brahe came along, okay, so he's got a bunch of really good data now. And so his assistant, Johannes Kepler, compared the actual data with the predictions of the mathematical model from Ptolemy, and they didn't line up. Okay, so he was able to prove conclusively that the geocentric theory of the universe did not work. Okay, so then he said, well, what does work? And so what he tried to do was he come up with models where the sun is in the central position and the various planets are going around the sun. And now that, in case we didn't talk about this last time, retrograde motion is explained by this model. Because if this is the Earth and this is Mars, okay, the Earth is in a smaller circle, it's moving faster. So if you're over here and you look at Mars and you see, okay, so Mars is over here and here's some background star. And when the Earth gets to here, Mars has moved, but not by as much. And when the Earth gets over here, Mars has moved by not as much. And what you'll see is that Mars will in fact appear to be moving backwards. It's not really moving backwards, but because the Earth is going faster than Mars is, if we look at Mars compared to the background stars, it will look like it's going backwards. Okay, so Johannes Kepler comes up with this, and what he found is that if these orbits are circles, it doesn't quite match the data that Brahe had gathered. So what he did then was he came up with his various assumptions, and he did this totally by guess and check. So the only way that he could get Brahe's data to match the numerical model was by making three assumptions. First one is that you assume that the orbits of the planets are ellipses, not circles. The second assumption is that you assume that the planets are moving faster when they're close to the sun and further and slower when they're further away. And he used this piece of pizza thing that we talked about last time too. He worded it in terms of pieces of pizza, but basically the important thing is that they move faster when they're close and slower when they're further away. But the last piece that he needed in order to make the data fit the model was this equation down here, Kepler's third law. And hopefully you remember what I said last time, is that Kepler arrived at this totally by guess and check. He tried squaring this and squaring that, didn't work. He tried cubing this and cubing that, didn't work. But the thing that finally did work was if he squared that and cubed that, okay, then all of a sudden everything fell into place. Then all of a sudden the data that Brahe had measured matched the numerical model. So Kepler knew that he was onto it, but he never knew why it worked. And that really bugged him. Even on his deathbed, that was one of his greatest regrets, is he never knew why these equations worked. He just knew that they did. And so guess what we are going to do today? Today, we are going to find out why they work. And the reason we can do it is not because we're smarter than Johannes Kepler was. The reason we can do it is because we have something that Johannes Kepler did not have. After Johannes Kepler died, a guy came along with the name that you've heard before, Isaac Newton, and he looked at Kepler's work and he did some thinking. And so he came up with a law. Now you might say to yourself, well, wait a minute, we already know Newton's laws. Newton's first law, Newton's second law, Newton's third law, we already have those. Well, Newton came up with another law. And so in theory, if you wanted, you could call it Newton's fourth law, but I don't know anybody who calls it that, okay? This other law that Newton came up with is called his law of universal gravitation. All right, so what Isaac Newton proposed, and he got this based off of what Kepler had come up with, was that Newton says that if you've got two objects where, here's one where, so let's call this M1, and here's some other object, M2, and these objects are separated by some distance, which we're going to call R, and notice that we're measuring from the center of M1 to the center of M2. That's really important. We always have to measure from the center. So what Isaac Newton proposed is that the force of gravity that attracts these two objects. So they might be, might be a star and a planet, might be a planet and its moon, it doesn't matter. He said that the force of gravity is proportional to the mass of one of the objects. Okay, so when I say proportional to, what that means is if you were to take this guy right here, M1, if you were to calculate, okay, so what is the force of gravity that's attracting these two guys? If you then replace M1 with another one where that is twice, sorry, not 22, but twice as massive, what you'll find is that the force now will be twice as much. And if you replace it with one that is 3 times as massive, then you'll find that the force is 3 times as much. So what we say then is that force of gravity is proportional to M1. Okay. And he's proposing that it doesn't matter which one you do it to. What you could do is you could leave M1 alone and then double the mass on M2. So the force of gravity is not only proportional to M1, it's also proportional to M2. Okay. And then Isaac Newton said, okay, well, what happens if you play with the distance? Okay, so let's say we've got one distance. Okay, so here's the distance. So this is R1. What happens if you take them out so that a new distance now is twice what they used to be? Okay, so it makes sense that the force of gravity that attracts them will be less. But Isaac Newton says that it will not just be 1/2. Isaac Newton said that the force of gravity is proportional to 1 over r squared. So what he's saying is that if you double the distance, then the force goes to 1/4 of what the original force was. And if you triple the distance, then the force goes to 1/9 of what it was. Okay, so Isaac Newton got these insights by looking at Kepler and Brahe's work. And so if we were to summarize this all in one statement, that statement would be that the force of gravity is proportional to, so that symbol that you see right there, the symbol looks like this, that means is proportional to. Okay, so Isaac Newton said that the force of gravity is proportional to M1, M2, and inversely proportional to r squared. Okay, now, I don't like proportional signs. I like equal signs. So if I want to replace that proportional sign with an equal sign, what do I have to do? Well, I have to put in a constant, because this could work if I put a constant in here and then M1, M2 over r squared, this constant, well, it could be a 2, could be a 5, could be 71, could be any number, and the proportionality rule would still be true. Okay, so this is something that you're going to see we're going to do a lot as the year goes on. We're going to start off with the observation that something is proportional to something else. And then we're going to say, let's get rid of the proportional sign. But the only way we can do that is by putting in a constant. And so then how do we figure out what the value of that constant is? Well, we do a bunch of experiments. So what we do is we take some mass where we know what the mass is because we've measured it. Take some other mass that we know what it is because we've measured it. We set them so that they are separated by a certain distance that we know what it is because we've measured it. And then we measure to see what is the force that attracts them. So as soon as we've done that, so if we know all of these numbers, well, then we can easily figure out, okay, we can calculate what this guy is because we know all of the other numbers. Now, Newton wanted to do that. But the trouble is, Newton wasn't able to come up with numbers for what M1, M2, and R and FG were. Actually, Newton probably did have a number for R, but he didn't have a number for the others. So he couldn't do it, right? But not too long after Newton died, along came a guy named Henry Cavendish. He figured out a really clever way to do it. He got this arrangement here where you see there, whoops, yeah, I have to turn on annotation before I go touching my screen here. Okay. So he's got a big heavy mass here and a big heavy mass here that are attached to a fixed platform. And then he's got something else that you can't really see very well in the picture here, but if you look over here, this is a top view of what he's got. So this mass here is the big heavy mass here. This little mass here is the thing that you can't see very well, but it's there. Okay. And so this, and let me clear this up here. So this, this thing that you're seeing right here, this thing can pivot. And it can pivot quite easily because it is hanging by a thread. Now, the picture didn't really show the thread. The thread kind of disappeared in the picture. So this here is a string, and the string is attached right here at the center of the mirror. And so that means that this thing that's hanging around the string here, it can pivot really easily. And so then what Henry Cavendish was able to do is that he took a known mass and another known mass, and he measured the distance between the centers of them. And then he could see that this one did get attracted here by a little bit, not very much, because the force of gravity is really weak if you have small masses like that. It wasn't very much, but he was able to measure it using a really clever technique. You see right here is a mirror. So if he shined a light on the mirror, and then he looked to see where did the reflection of that light appear from, even if this angle here was a really small angle, if he shined the light on the wall and the wall was really far away, he could measure it. Okay, so it was really clever. The people that lived a long time ago, they didn't have the fancy equipment that we have today, and yet they figured out super clever ways to come up with stuff. So Henry Cavendish then was able to make all the measurements, and he was able to come up with a number for what this proportionality constant is, which, by the way, notice that instead of calling it K, we're calling it big G. We're doing that because it is such an important number that it deserves its own letter, right? So big G is a number that we had to measure experimentally. And so this is the value. And so in your homework tonight, they're going to start off with some really easy questions. They're going to say, all right, assume that you've got some object right here. Let me switch to a different color pen so you can see it a little better. Assume that you've got some object here, like maybe it's the sun, and you've got some other object here that is some planet, and you know what the distance between the two of them is. Okay, so what is the force? How many newtons of force are attracting these guys? Okay, so if you use table 7.1, you can get all the information you need. So here's the sun, here's the mass of the sun, here's whatever planet you might be interested in, and here is the average distance of the planet from the sun. So bingo, you're good. Okay. Now, when you read the book, you are going to see that in the book, they say that G is equal to 6.67 times 10 to the negative 11th. So you're saying, where did all these extra digits come from? How did we know what they were? Well, this is where they came from. Let me start right here. Okay, so if you take your physics book, turn it to the back, open it up, you'll see a bunch of really useful information, especially right here. There's numbers in here that are going to come in very handy as the year goes on. Things like the mass of an electron and the charge of an electron. And Avogadro's number is actually, we're not going to be using Avogadro's number in this class, but it's all sorts of important constants are in here. And if you look at about the 8th one down, you'll see there's big G. And you can see the number is given there with a whole bunch of extra sig figs. So if in your problems you ever need to know what is big G and you need more than 3 sig figs, look in here and you can get it from here. Now, while we're in here, let me point out something really important. If you take this page and you flip it back one more, you'll see a table right here, and that table is going to be very important. You need to know how to read that table. So what I've done here is I have put a copy of that table in my PowerPoint presentation here. This table has not only the information that we had from this previous table here, but it's also got a whole bunch of other stuff that that's going to come in handy. Except that it calls things a little bit different. And so what I found over the years is the students have a little trouble interpreting this table just because the wording that they use is a little bit unfamiliar with you. So let's talk about things here. Let's suppose I want to know what is the average distance of the planet Saturn away from the sun. All right, so I come over here and I see, okay, well, there's Saturn. And here's all sorts of stuff about Saturn. And so here's a list of what that stuff is. So I just look here to find out where does it tell me what is the average distance. And I quickly realize, wait a minute, nowhere in here does it ever say average distance. But I'm sure that one of those numbers must be the average distance. They're just calling it something else. Well, it turns out this is it right here. The semi-major axis. That is the average distance. So let's take a minute and let's talk about what is a semi-major axis. Okay, so remember when we talked about ellipses, we said that ellipses have two focus points. Okay, so if I were to take a peg and put a peg on the wall, take another peg, put the other peg on the wall, and now I take a string and I tie it in a loop. So I have a loop of string. And I take my pen, so I loop the string around. Let me switch that to a different color here. Okay, so I loop the string around here, and then I take my pen and I put my pen as far away as the string will allow me to do it. And then I move my pen around. So now my pen gets here. And I'm always keeping my pen as far away from the pegs as the string will allow me to do it. So when I get over here, the string looks like this. Okay, and then when I get up here, the string looks like this. Okay, so I'm going to trace the pen around in a path, keeping the pen as far away from the pegs as the string will allow me to do. So when I do that, and let me see if I can get a little better here. So I will come up with a shape that will look something like this, and that is an ellipse. And where those two pegs were, those are the focus points of the ellipse. Now, if I were to draw a line going from one side of the ellipse to the other side of the ellipse, you'll see that line is going to be different lengths depending on where I draw it. If I draw the line that goes through the two focus points, that one is the longest one that I can get. And if I draw the line going through like this, that one is the shortest that I can get. Okay, so let's focus in on that one that's the longest that I can get. That line has a special name. That line is called the major axis. And then the shortest one, that's called the minor axis. All right, so you see this term here that I claim is the same thing as the average distance of the planet away from the sun. Well, that's not the major axis, that's the semi-major axis. So what that means is we're going to take half of the major axis. So this distance right here, half of the major axis, that is the semi-major axis. So I claim to you that that distance, the semi-major axis, that is the average distance of the planet as it goes around the sun. Okay, so let's look at it. So remember that one of Kepler's first law says that the sun is located at one of the focus points. Okay, so if this is the sun right here, okay, when the planet is over here, you can see that this distance here is less than the semi-major axis. When the planet's over here, this distance is more than the semi-major axis. So it's easy to believe the possibility that if you were to take the average of all these distances as the planet goes all the way around the sun, it's plausible that the average distance might be equal to half of the major axis. Now, I'm not going to take the time to prove that. I don't think that would be a useful way to spend our limited time. So I'm just going to say without proving that that is in fact the case. So if you ever need to know the distance of some planet from the sun, just look on this table, look for the semi-major axis, and that will be it. And if you ever need to know the average distance of the moon away from the Earth, look on this table down here. Look for the semi-major axis, and bingo, that will be it. Okay. Now, you do need to be a little careful with this table because this table can fool a lot of people. So let's suppose we want to know what is the average distance of Saturn away from the sun. So we find Saturn, we find the semi-major axis, we come down here and we see 1,433.5 something. Let's just call it 1,433. Okay. So you might wait, you look at that and you say, wait a minute, there's no way that Saturn could be only 1,433 meters away from the sun. That cannot be. Well, you'd be right in thinking that. If you look right here, you'll see it says kilometers times 10 to the 6. So what that means is we have to take our 1,433, times it by 10 to the 6, and note that the units there are going to be kilometers. So Saturn is actually 1,433 times 10 to the 6 kilometers away from the sun. Okay, so you see how that works? You're good on that? Okay, now I do need to warn you that kilometers are not a standard physics unit. What is the standard physics unit for distance? It's the meter. Now, if you're using Kepler's third law, you don't care. Because in Kepler's third law, you're going to take the average distance divided by the average distance of the other object, okay, cubed. So as long as you've got one divided by the other, if you want to use kilometers on top, you can, as long as you use kilometers on the bottom too. So if you're using Kepler's third law, you don't care whether or not you're using standard physics units. But we're going to be deriving some equations today where it will be important that we use standard physics units. Okay, well, what I'm about to do is I am going to I'm going to do the thing that Kepler wished all of his life that he could have done. Okay, I am going to derive Kepler's third law. And I would recommend you take careful notes about what I'm about to do, because you guys know by now how important I think derivations are. Deriving stuff is what makes physics physics. We don't want to just take equations that we don't know where they came from. We need to know where the equations came from. That is the heart of physics. So when we take our test right after the Thanksgiving break, it's entirely possible that deriving Kepler's third law, might be a question on the test. Wink, wink, nudge, nudge. So I recommend that you take careful notes. Now, what I'm about to do, I'm going to do it fairly fast, and you might have a little trouble keeping up. If you have trouble keeping up, remember that everything that I'm about to do is being recorded. And I will post this recording on Canvas. So if you have trouble keeping up, well, that's okay. Just go back and watch the recording. Okay. All right. So I want everybody to open up to a new page in your notebook. And up at the top, I want you to write derivation of Kepler's third law and a couple other useful equations. Because what's going to happen is, along the way, as we're trying to get Kepler's third law, we're going to come up with a few other equations that you are going to find very helpful in tonight's homework. In fact, you're going to find that they are essential for doing tonight's homework. So the derivation I'm about to do is kind of long, but it's very important. All right, so let's start into the derivation of Kepler's third law. and a few other useful equations along the way. So what I'm going to do is I'm going to first just remind you what we did a while back. One of our homework problems a while ago was we had this person who was swinging this mass above their head in a horizontal circle, and we wanted to calculate what was the tension of the rope that held it in place. Remember that problem? Okay. Now, if he's swinging that thing fast enough, then the rope here is going to be very close to being horizontal. Now, it won't be perfectly horizontal because you've always got gravity pulling down on it. But if he swings it really fast, it'll be really close to being horizontal. But tell you what, let's let it be 100% horizontal. Let's assume that this guy is a spaceman in outer space. So let's give him here's his space helmet. Okay, so he can breathe. Okay, so he's in outer space. So he's in zero gravity. Okay, so this is a perfectly horizontal string now. So we don't need to do any approximations. That string is 100% perfectly horizontal. So if I want to calculate what is the tension in that string, well, if I do my free body diagram, the one and only force that's acting on that mass is the string. He's in outer space, so there is no gravity. All right, so if I want to use Newton's second law, so I'm going to say sigma F equals ma. Well, there is only one force, and that force is tension. And that's equal to mass times the acceleration. Now, if this object is moving at constant speed, is it accelerating? Answer yes, because the direction is changing, right? What equation will tell us what the acceleration is? Well, v squared over r. Okay, so the tension in that string is equal to the amount of mass that we have at the end of the string times v squared over r. So hopefully you guys remember doing that one. Now, let's look at this. I've got a planet. It's going around the sun. What is it that's holding the planet in place? It's not a string, it's gravity. So the force of gravity, that is what's acting in place of the string. That's what's keeping the planet in place. And so if we do the exact same thing that we just got through doing, if we say sigma F for the planet here is the mass of the planet times the acceleration of the planet, well, it's not tension this time. This time, it's the force of gravity. So the force of gravity is equal to the mass of the planet times the acceleration, which is going to be the same as it was before. It's going to be v squared over r. Okay. Now, here is the thing where we have the advantage over Johannes Kepler. We have Newton's law of universal gravitation. Okay, we know that the force of gravity is equal to big G times m1 times m2 over r squared. Johannes Kepler didn't have that. And so that's all we need. All right, so let's replace force of gravity with big G times m1, m2 divided by the distance squared. So that's equal to the mass times v squared over r. Now, remember, this mass here is the mass of the planet. So tell you what here, on our m's here, instead of calling it m1 and m2, let's call this the mass of the sun times the mass of the planet. And this mass over here is the mass of the planet. Notice that the mass of the planet cancels out. Okay, so it doesn't matter what the mass of the planet is. You could have a little tiny planet orbiting, and you could have a great big huge massive planet orbiting, and as long as they're both orbiting at the same distance, then it all works out, even though they have very different masses. The mass of the planet does not matter. Okay, now if you look over on the right side, you'll see we've got an r, and on the left side we got an r squared. So if we were to multiply both sides by r, This R cancels that R, this R cancels one of those R's, but not the other one. So if we then come up here, so what we're going to have is we're going to have V squared equals G times the mass of the sun divided by the distance between the planet and the sun. And if I now square root both sides, I'm going to get that the velocity of the planet is equal to the square root of big G times the mass of the sun, not the mass of the planet, divided by the distance from the planet to the sun. And remember, that's the distance from the center of the planet to the center of the sun. So this is a very, very useful equation. It's not Kepler's third law, so we're not finished yet. But I'm going to temporarily stop here because this is a super important equation that you are going to need when you do tonight's homework. They're going to ask you questions like they're going to say, okay, I've got some planet orbiting some star, and I know the distance of the planet is some number. They'll tell you what the number is. And they'll say the mass of the star is some number. They'll tell you what the mass of the planet star is. And they're going to ask you to calculate what is the speed of the planet. Okay. Now, we derived this assuming that the planet was going in a circular orbit. And hopefully you guys remember that Kepler said that's not what happens. They're actually elliptical orbits. So this V here is going to be the average velocity. Okay, so when the planet is a little bit closer to the sun, it'll be going a little faster than this. If it's a little bit further away from the sun, it'll be going a little bit slower than this. But this is the average velocity of the planet. Okay, and if you're going in a circular orbit, that is in fact equal to the velocity. Okay. Now let's see how we might use this. So here's the equation we just came up with. And when you read the book before you do the homework, because I know you always read the book before you do the homework, right? They're going to talk about a thought experiment that Newton came up with. He said, if you were to take a cannon and you were to place it up on top of a really tall mountain, and you were to shoot that cannon, okay, there is a speed where if you shoot it at this right speed here, the cannonball will go all the way around the Earth in a circular orbit, and then it'll come back and it'll hit you in the back of the head after it's gone around. And this equation right here tells you what is that magic speed. I like to call this VC, where C stands for critical. This is the critical velocity. If the velocity of that cannonball is less than the critical velocity, you can see here what's going to happen. The cannonball is not going to make it all the way around the Earth. It's going to fall and it's going to hit the Earth. Now, it might go a little bit farther, you know, but if it's anything less than the critical velocity, it is not going to make it all the way around the Earth. Okay? If V is less than VC, then boom, it hits the Earth. If the velocity is equal to VC, then you will have a circular orbit. Oops, circular orbit. Now, here is the big question. What happens if the velocity is greater than VC? Anybody want to unmute yourself and tell me, what do you think is going to happen if the velocity is greater than VC?
Won't it shoot off into space?
Okay, will it come back?
It'll just fly off into the distance, right?
Well, I can see why you might think that, but actually what happens is this right here, okay? Assuming that it's not a whole lot greater. Now, you are right, there is a thing that's called escape velocity. And so if the velocity of the cannonball is way greater than VC, it will go flying off into space and it will never come back. But it has to be way greater in order for that to happen. Most of the time, what's going to happen is this, okay? It does go flying off into space. So you'll see it's getting, as it goes around here, it's getting higher and higher and higher above the Earth's surface. But when it gets to the opposite side of the world, it reaches the highest point that it's ever going to get. And then it starts coming back. Okay, and then it'll come around, it'll hit you back, it'll hit you in the back of the head, just like it did if it was a circular orbit. And so what shape is this going to be? Well, hey, it works out to be an elliptical orbit. Okay, elliptical orbit. Okay, so if the velocity of the cannonball is greater than VC, but less than VE, where VE stands for the escape velocity, then what you'll have is you'll have an elliptical orbit. And that is in fact what pretty much all of the orbits are. All of the planets as they go around the sun, they're all elliptical orbits, because what are the odds that they're moving at exactly the right speed in order for it to be a circular orbit? I mean, the odds are so small that you can basically say zero, okay? So it's going to be an elliptical orbit. But there is a number that we do have to be careful not to exceed, because if we go too much, then it will go off in space and never come back, and that's called escape velocity. But we're not going to talk about escape velocity in this class, because in order to calculate what the escape velocity is, you need to know calculus. Now, I recognize that some of you do know calculus, but most of you don't, and I don't want to take the time to go into it right now. So we're not going to worry about escape velocity in this class. We're just going to assume that it's bigger than the critical velocity, but not so much that it exceeds the escape velocity. Okay, so this equation that you see right here is going to come in really handy in tonight's homework. They're going to give you questions where you're going to need to use this equation. But remember, whenever you're using this equation, the number you put in for R must be meters, cannot be kilometers. The number you put in for the mass must be kilograms, cannot be anything else. Anything you put into this equation must be standard physics units. And so the velocity then will work out to be meters per second. Okay. This is different from Kepler's third law. In Kepler's third law, you can get away with using non-standard physics units. But for this equation, you absolutely positively must use standard physics units. It will not work if you don't. Okay, now, our goal was to derive Kepler's third law. We obviously are not there yet. So let's continue on. Let's take this thing and let's work with it and see maybe we can transform this into Kepler's third law. So let's go back to work here. So what I'm going to do is I'm going to ask myself, in fact, let's go back to the circular case because it's a little bit easier to do this. And let's go back to the circular case here. Okay. So I want to know if I've got, oops, I keep forgetting that I need to turn on annotation before I go touching my screen. Okay. So if I've got an object right here that's moving at a velocity v and it's going in a circular orbit, how much time does it take to go all the way around? Well, we can figure that out. We know that if you're going in a circular orbit, we know that the total distance that you travel is 2 pi times the radius of that circle. So from the center of the circle out, okay, that's the distance. And so if we're moving at a rate that is equal to a number that we're going to call v, and we know that distance equals rate times time, so the distance is 2 pi times the radius. So this r is rate, not radius. So the distance is 2 pi r, the rate is velocity. The time that it takes, well, that's not just any old time, that's one very special time. That's called the period. And so do you remember the other day when I said that lowercase t is what we use for any old time, but uppercase t is one very special time. Uppercase t is the period. All right, so from the dirt equation, we can get 2 pi r equals vt. And then what we can do then is we can solve that for v. So we get the velocity equals 2 pi, that's supposed to be a pi, 2 pi times the radius of the circle divided by the period. Okay, so wherever I see a v over on the right side, I can just replace that with what I know that v is equal to. And I'm thinking we're going to come up with a very useful equation. All right, so what I'm going to get is 2 pi r divided by the period equals the square root of big G times the mass of, in this case, it's the Earth, but it could be a planet going around the sun. So rather than calling it ME, I would prefer to call it MC, where C stands for whatever is the object in the center of the circle, that the thing that the other object is orbiting around. Okay, so I'm going to divide that by R. Okay, so if I manipulate this a little bit, I can come up with another really useful equation, which still isn't yet Kepler's third law, but it will be very useful in your homework tonight. So how about let's flip both sides. So that's going to give me T divided by 2 pi R equals the square root of R over G times the mass of whatever is the object in the middle. Okay. And so now if I multiply both sides by 2 pi R, so that cancels that. So now I'm left with the period of the object is equal to 2 pi R times the square root of, let me clear a little space here. Okay. Times the square root of R divided by big G divided by big M. Okay. All right. This is a really useful equation that you are going to find will come in very handy for solving some of tonight's homework problems. But when you look in the book, you're going to find out that they didn't write it this way. In the book, they wrote it as 2 pi times the square root of R cubed over GM. So how did they go from this to this? Well, they just took the R inside the square root sign. You know that R is the same thing as the square root of R squared, right? So if I replace R with the square root of R squared, then I can bring the R squared inside the square root sign. And if I've already got an R there and I multiply by an R squared, that's how I get the R cubed. Okay, so here we have yet another equation, which is not yet Kepler's third law, but by the way, we're getting really close. We are almost there, okay? But let's pause for a second because this is going to be really, really, really useful in your homework tonight. So what they're going to do is they're going to say, okay, I have a satellite that is orbiting at a certain distance above the center of the Earth. And I know that it's the Earth, so I can look up in the table to find out what the mass of the Earth is. And then they're going to ask you to calculate what is the period of that satellite. Okay. Or they might do it the other way around. They might tell you what the period is and ask you to calculate what the distance is. It doesn't matter. I mean, these three variables right here, R, M, and T, as long as you know any two of the three, you can then calculate what the other one is. All right, so what we have here are two extremely important equations. This equation right here, and then the other equation, which was period equals 2 pi square root of R cubed over GM. These two equations are going to be super, super helpful in tonight's homework. But we're not yet to Kepler's third law. And we're running low on time, so you might be getting worried, but don't worry. We are almost there. We are super close. Okay, so what I'm going to do is I'm going to take this equation that we have here, and I'm going to square both sides. So I'm going to square this side, and I'm going to square this side. And then I'm going to move it all up here. Okay, so what I'm going to get then is t squared. Whoops, hang on a second here. Okay, so I'm going to get t. My touch screen works a little bit funny. If I go too close to the edge there, it does weird stuff. Okay, so t squared equals, so 2 pi squared, well, that's 4, because 2 squared is 4, right? It's pi squared So if I square the stuff underneath the square root, well, the square root goes away. So I'm left with r cubed over gm. Now what I'm going to do is I'm just going to divide both sides by r cubed. So that goes away. And so what I'm left with is t squared divided by r cubed equals 4 times pi squared divided by g, and also divided by the mass of whatever it is that's in the center of the center there. Okay. Now, believe it or not, this is Kepler's third law. Now you might say to yourself, well, wait a minute, the left side looks like Kepler's third law, but the right side does not look like Kepler's third law. What's going on here? Well, here's what's going on. Let's suppose that I have one object that is right here, and I'm going to call this object A. And let's see, tell you what, let me clean up my picture here. Okay, let me come in here. And so what I'm going to do is I'm going to assume that object A is at a distance of RA. So that distance there is RA. And then I'm going to say, okay, I've got another object here. And this is object B. And object B is at a distance RB away from the sun. So when I did my t squared over r cubed here, it doesn't matter whether it's object A or object B. I could say TA squared over RA cubed, and what I'll get is I'll get 4 times pi squared over GM. Or it doesn't have to be object A. It could be object B. What I could do is I could do the period of planet B squared divided by the distance of planet B squared, or cubed. And what I'll get is I'll get the exact same thing. Okay, so regardless of whether it's A or B, the ratio of the period squared over the distance cubed is always going to be 4 pi squared over GM. So as long as planet A and planet B are both orbiting the same sun, or if it's not a sun, if it's a planet, as long as satellite A and satellite B are both orbiting the same planet, then this value right here will always be the same. So the period of planet A squared divided by the period of planet B squared is going to equal to the distance of planet A cubed divided by the distance of planet B cubed. As long as they're both orbiting the same central object, bingo, Kepler's law works. Okay, so we have just derived Kepler's third law. And along the way, we came up with some really useful equations. Okay, so if you guys, so these equations that you see right here, these are your friends. These are the equations that are going to help you do tonight's homework. Okay. All right, so I realize I hit you with an awful lot of stuff. And we've only got about 2 minutes left, so you don't really have questions or time to ask questions. But anybody want to sneak in one real quick question, or do you want to just type bye in the chat box and see you later? Oh, I guess you probably want to know what the homework is, right? Okay, let me just tell you real quick what the homework is. Here it is. So problems 6 through 14 in chapter 7. Don't forget to take today's daily quiz in sometime before we meet again. Also, don't forget that there is going to be a tutoring session tonight from 3:45 until 5 o'clock. Check your email, and I'll tell you via email whether that tutoring session is going to be held in this Zoom room here or in a different Zoom room. Okay, well, time to leave. So I'll see you guys later. And I'll go ahead and end the recording.